cross check whether it should be 16. Go back to your chart. So V4 to V1 is 6. Then somebody from this side, V1 to V3 is what? V3 to V2 is sorry, did I make V3 to V2 is what? 7. So 6 plus 3 plus 7 is? Okay? So you know how to do this now? Given a graph, you have to go through these iterations where you pick a row and column. Okay? So it's an idea to take home, right? So same thing for 5 vertices. Alright, so I will give you just the weight matrix because you cannot represent all the weights within the edges. So, but of course you can construct the graph if you want to given the weight matrix. Why? Because if the weight is infinity, it means they don't have an edge. Right? So if V1 to V4, there's no edge. So that's why the weight is infinity. But the others, they have, like V1 to V2 is 3, then V1 to V3 edge weight is 8, and V1 to V5 is -4. Alright? So given the weight matrix, you can also come up with what? The predecessor matrix. Because if you have edge weights, that means they are connected to start with. So V1 to V2, the edge weight is 3, so the predecessor is also V1, right? You understand what does it mean? Because there's a positive edge weight, or positive or negative, it doesn't matter. There is a non-zero, non-infinity edge weight. So V1 to V2, the predecessor is V1. Similarly, V1 to V3 is V1. Then why this is not applicable? Because the weight is infinity. So V1 to V4, the weight is infinity, so it means there's no edge to start with. That's not applicable, and this is why V1 to V5, there's an edge of weight -4. So it's okay to have negative weight edges here. So we will have V1 as the predecessor. So that's how we fill up the predecessor matrix. So similarly, V2 to V1 is infinity, which means what? No edge. So there's no predecessor, not applicable. V2 to V3 again, there's no edge, so it's not applicable. Of course, from the vertex to itself to start with, it's all zeros. Okay? So you can also have not applicable for the leading line. And then V2 to V4, it is 1, which means there is an edge. So what's the predecessor from V2 to V4? V2 to V4. To start with, you can directly reach from V2 to V4. So what's the predecessor? V2 itself. And from V2 to V5, some weight, 7, right? So you can reach from V2 to V5 directly to start with. So the predecessor is going to be V7. Okay, so that's how you initialize the predecessor matrix. So given the weight matrix and the predecessor matrix now, so you can go through the iteration, right? So it starts with what? The first row and column. Okay? So you will add up the entries. 0, can you reduce the 0? How do you check that? Somebody other 3 infinity is 0. The infinity side. So it's less than 0, right? Then what about this? Okay. So you join the club. So somebody other than those 3. What about this 1? 7, isn't it? So we can just leave it as it is. This 4. No. Yeah. So now you know at least a trick. You could check it each time, but if you have infinity in one of the two, you see in this row you have infinity, right? Right. So you are basically going to add infinity with anything here, isn't it? Infinity with 3, infinity with 8, infinity with infinity, infinity with negative 4. If you add infinity to anything, it's going to be infinity, right? So which means you know you are not going to reduce anything in this row, right? So in the next one you can write the same thing as it is, blindly, without even checking each of them. If you are adding infinity with something, it's not going to change. You see what I mean? Similarly, in the last you see infinity here. So none of these are going to change. So can I say infinity 26 to you? That will save some time. So similarly, the predecessor entries should not change if you don't change here. So change the predecessor entries only if you change anything here. Is that clear? So let's see. Now we have a 2 here. So there is possibility of some change, provided again you should not have infinity here. So what about this infinity here, other than those 3?
Reduce it by.
Huh?
Reduce it by.
Change to what? 2 and 3 is? 5. So it is 5. And what should be the predecessor here? You're changing this is the thing, column, and this is the row, right? So it's going to be V1. You see what I mean? Yeah. So you always look for the flat, the row. This is the row, the highlighted row. The highlighted row, whatever is the entry from where you are adding. So this is the highlighted row, right? And the entry you are adding, this is this cell. In this cell, what is the value here? Which is V1. That's the value. Okay? Look for a highlighted row and whatever the value in that cell is V1. Okay? And what about this? This is negative 5 to start with. Can you change it, reduce it further? No. 2 and 8 is 10. What about this? Is infinity. He's probably joined the club, so somebody else.
Can be reduced to -2.
Negative?
To -2.
Why?
Because -4 plus 2.
Negative 4 plus 2 is negative 2. So what should be the predecessor here? V1, because this row is changed based on this. Negative. The value. Yeah, don't look at this thing. Okay, so the corresponding entry is V1. Okay? So now how to do, you know how to do this, right? So let's just trace the path one more time. So let's say from V3 to V1. You want to trace the path from V3 to V1. Once you do all these iterations, 5 iterations, you obtain the weight matrix and the predecessor matrix. So using the predecessor matrix, you want to trace the path from V3 to V1. So let's do that. So looking at the predecessor matrix, you tell me what's the predecessor from V3 to V1. How do you do that? V3 to V1, the predecessor right now before V1 is V4. So somebody else from V3 to V4. You see what we are doing here, right? You want to find the path from V3 to V1. The predecessor matrix is going to give the right immediate predecessor before the end vertex, which is V1. So from V3 to V1 it says what? V4, right? So V4 is the immediate predecessor to V1. So this is a direct edge. So now we want to find the path from V3 to V4 to see what's the predecessor before V4 on the path from V3 to V4. So what is that? V2. V2. So V2 is the direct edge, V2 to V4. So now V3 to V2. What's the predecessor from V3 to V2? V3, which means it's direct edge. Right? V3 to V2, the predecessor is V3 itself. So it is. So what's the path weight? From V3 to V1, what's the path weight? V3 to V1, how to find the path weight? V3 to V1, right? 7. That's the final distance matrix, right? The final weight matrix, that is 7. So the total path is of weight 7. How do you cross check? Go to the original weight matrix given to you. What is given to you? This weight matrix. So you have to look at, can you come up with now the edge weights from this? What is the edge weight from V3 to V2? 4. From V2 to V4? V4 to V1? 2. We should add up to 7. Okay? Clear? Can do this now. What? So let's what is it? Just the introduction to start with, so we'll continue with this next time, but let me just introduce this distributed systems. So what do you mean by distributed? Anybody has any idea?
What now?
What is meant by distributed system? Huh? No. I'm not distributing. Have you heard of parallel computers? Parallel computer or supercomputer? You heard of supercomputer, right? A supercomputer is what? It's a computer by itself, but it has a lot of processors. You know what a processor is, right? So it has lots of processors. Whereas a distributed system is a typical computer where you have several such computers connected in a network. Okay? So a distributed system is a network of computers, a regular computer, not like a supercomputer with multiple processors. So with one supercomputer you have multiple processors that can do jobs in parallel and give you the results quickly. Whereas here we can do the same thing by letting the different computers to do the different jobs in parallel and then bring together all the results. Okay? So one classical example we can always use is matrix multiplication. What's the idea in matrix multiplication you did for your exam before, right? So you can multiply the different rows and add them, what? When you're multiplying the elements of this row and column, you can also multiply and add something else, right? So if you can assign each row to each computer, they can do the multiplication simultaneously and get you the results, the product matrix quickly. Okay? So which means you can get the result quickly. So that's what I say by higher throughput. Throughput means how much, like at what speed you can get the results, right? If it takes like, if you do everything, all these multiplications in one computer, it may take say 10 seconds. But if you do all these things in all these computers, it may take only 3 or 4 seconds. So that's the speed up you get. Okay? And we can get this at lower cost because all these computers are regular computers. We don't need any sophisticated computers. Okay? So the key thing is all these computers have to communicate, exchange messages, like you're splitting this matrix and sending out and then they're getting back all those results and all those things. So there's a lot of communication on the network. And so if they communicate and interact, it's going to be lower cost because you don't need any sophisticated computers. You can get quick results. Okay? Is that clear? And we can also share resources. You probably have realized this. You go to the lab, you don't have a printer connected to each of the computers. You have only one printer out there, and all the computers can print with that printer. So that's also a kind of distributed system where you're sharing the resources. Okay, so the printer, the hardware is shared by all the computers, and you can print from any computer at any time. Okay, so of course, if the printer gets more than one print command, it's queuing up all the commands. So you can print only one at a time. So you have some queuing at the printer also. Okay, and same thing, you can share software. You might have heard of this, what is that, all this cloud computing, that's a distributed system. Well, Microsoft Office has a 365 now, so that's a distributed, the Office is in the cloud. You don't need to have your Office installed on your computer. So the software is being shared by all the clients, all the users. Okay? There's also this fault tolerance. Fault tolerance means if even one of these multiple computers fail, the other computers can still do the job. So the whole thing is not getting shut down because of failure of one computer. You see what I mean? So whereas in a single system, if something happens to a system, then you cannot do anything. Even if it's a multi-processor, if some failure can impact all the processes, then the whole thing is shut down. Whereas here, failure of one computer or even one wire connecting some computers fail, then the others can still communicate. Right? So we have a lot of reliability and availability. The others are still available to do some job for you. Okay? So there are several issues in this distributed systems. Typically we will deal with the absence of a clock. That's one thing that we will be focusing on, at least to start with. Which means all these computers, they have their own clock, right? You know what a clock is, right? Typical clock. And you cannot precisely say this is the time for this whole system. Now, it's a system now, it's a collection of computers, right? So each computer has its own clock value. Even though you can say the clock value is the same, to the minute precision, you cannot say all the clocks show the same value. Because each computer, the clock can drift. Drift means the rate at which things change can differ by a slight amount. Okay? So, and another issue is shared memory. Because suppose you have now different computers. It's not one single computer and one single memory that is being shared. So each computer has its own memory. So you don't have one common memory that can be accessed by all these computers. Right? So the memory is distributed also. So the key thing is they have to communicate, exchange a lot of messages. And when you send messages over the network, the delay can be arbitrary. It may take, depends on the traffic in the network. So it may take 2 seconds one time, and it may take 10 seconds another time between two computers. So the delay between any two computers can be arbitrary. So a lot of issues are there to be handled. So we'll focus more on the messages and the clock, and look at some problems from next time. Okay? So I posted some slides in the website. I'll be updating some more slides.